So let's do some of these standard machine learning projects. I just want to point them to you. So prompt injection you've seen. And by the way, if you want just a formal lecture kind of thing, I highly recommend Google Learning. You can go to these Google badges and watch videos and take little quizzes, and it's very good, introducing you to the types of AI and general concepts. That's good. But what I want to do now is demonstrate how this works in Python. So starting at ML 100, you can tell from the number, this is what I first did in machine learning. So we're going to do some real machine learning, not a large language model, but a project we make ourselves in Python. And for this, I'm using Google Colab. You can use any Python environment you want, but Google Colab is the free online one Google provides. And I really like it because every student has access to it. They don't need any special hardware. As long as you have a web browser, you've got this environment. And so you make a new notebook. All you need is a browser and a Google account of any kind. And now you can put code here. And by the way, it has some generate your code with AI thing I have never tried. But anyway, we're going to put in code. So first, we're going to just import TensorFlow, which is the library we're going to use. And you'll see it's very easy to make machine learning with Python for the same reason everything is easy in Python, because other people have written libraries and you're just using their libraries. So when you run this, make it bigger there, it's just going to import the TensorFlow library and then print a version number so I know it worked. And still going 8 seconds, taking longer than usual. But of course, okay, there it is. That version number. It doesn't matter for us what version number is. So now we have TensorFlow. So now, if I have a linear relationship, if I have some data like x goes -1, 0, 1, 2, 3, and y is -3, -1, 1, 3, 5, 7. This is what science was when I did it. You measure something like pressure and temperature, and then you try to draw a graph and find the trend. So you look at this, a human can look at this, and you notice every time x goes up by 1, y goes up by 2. And when x is 0, y is -1. So here's the relationship, y is 2x minus 1. That's the formula that makes these numbers. And in the old-fashioned technique, a human could write a program to generate these numbers, and they would have to put this equation in there. But we're going to make AI, it's going to figure out that relationship without us explicitly programming it. And as you can see, it only takes about 12 lines of code to do that. So here's the code. I'll make another block here and put it down there. So it imports some libraries. Now it makes a model, and this model is a neural net that contains one neuron here, and it's going to take the X data and the Y data, and then it's just going to fit the model doing 500 steps. Now I'll run it and I'll talk about how this works. It has 2 parameters, which is the slope and intercept, and it starts them at random values, and then it does stochastic gradient descent, which is it can do a partial derivative, and it can figure out for small motions which direction will cause the loss function to go down. So it defines a loss function, which is typically the square of the y error for every point. How much did you miss the points by? That's this loss function here. And so let's see if I can get this to show up there. Here's the results. See, this is it did 500 steps called epochs here. And there we go. And so it started, let's see, there we are, epoch 1. There. The loss was 10. So it figured out which direction would make the loss go down and took a little step. That brought it down to 8, down to 6, down to 5. It made hundreds of steps going down. That is stochastic gradient descent. Each place it stops, it does a partial derivative where it is to figure out which direction will cause the loss to go down, and it takes a little step in that direction. And after a while, the loss went down to essentially 0. It went down to something like 10 to the -4 or 10 to the -5 here, a very small number. And so when it was done, to evaluate how well it worked, I had it predict the value at 10. And the right answer is 19, 2 times x minus 1. And see, it got 18.98. So it got very good at predicting the value. And we can also, here's what it looks like. Your x comes in, it calculates mx plus c. M and c are the adjustable parameters, and calculates y. And it learned to have m equals 2 and c equals -1 from the data. So if we if you want to see what it learned, this will do it again. And then at the end, instead of just showing me the prediction, it's going to show me the weights. The weights are those parameters, M and C. So I'll put this one in here and run it. There it goes. And of course, for this simple task with only a few points, it doesn't take very long to do any of this. So here's what it learned. This number is almost 2, and this number is almost -1. So you can see it's within 1% of the right answer in the slope and the intercept. So that's machine learning. It has learned a pattern without me programming in that formula, 2x minus 1. So now we can add some errors. If we put some errors in the data here, we can go back up to the code. See if page up's going to work. It is. All right. There. And so I'm going to put in this data, which has errors in it. I'm going to comment out that line. So all this is the same y values plus or minus a little bit of error. So now when you run that one, the loss is going to start at some high value. You see the loss is going down, down, down. Now before the loss went down to 10 to the -4, but now because of the error, the loss can't get that small. Even the best fit has like 0.004 error. But again, it did pretty well. The right answer is 2 and -1. And as you can see, it's again within 1% of the right answer. So a little bit of noise didn't affect it. Now, suppose we put in data that does not fit a straight line at all. This is a parabola, x squared minus 4x minus 5. So it can't do a good job fitting this at all. It will try to fit a straight line through it. Let's get back to the code. All right. So now I'm going to comment out that one and put in this one, which is wildly different data. Now the loss is 21, 8, 0.4, 0.1, 0.04. Get down to like 0.06, 0.05. All right. So it, again, gets down to 0.004. That's funny. I'm getting the same answer. I think something went wrong with my code up here. Maybe my copy and paste didn't put in the right data. Oh, that's the wrong data. Yep, my copy and paste didn't work. All right. There's what I should have had. Copy. And here's what I should have here. All right. That's more like it. That should, because the loss should not be able to get very small anymore. Now the loss is like 98.76. And I think the loss can never get below 4 now, because no straight line will really go through that curve very well at all. And of course, it's not going to get the expected values. It's getting -1 and -5. It's fitting some crazy line that doesn't fit it very well. So if you wanted to fit a more complicated curve, you'd have to have a model with more neurons. So here, this is one that's going to fit a sine wave. I have cosine times 0.1 plus a random noise. And I multiply x times cosine x. So this is a curve. And I think I'll just make a new notebook here to clean off my old one. I'm going to move to trash, return, new notebook. And I got a nice clean notebook with nothing in it. And now I put in this code. And this is going to fit. Now, this is going to use a much more complicated model. Instead of one neuron, it's going to have one input neuron. Then it's going to go into 64 hidden neurons in a layer and another layer of 64 neurons. These are the ones that do the calculation. And then one more neuron for the output. So I have 128 hidden neurons in between input and output that can be adjusted. So if you look at the model, this is 2 parameters for slope and intercept. Here's 128 parameters for the slope and intercept of all those 64. Here's 41,060 parameters because you have all those 64 feed into each of these next layer of 64. So it's something like 64 squared parameters, and then the output. So the total model has 4,300 parameters. So that's enough to fit a really complicated shape. And you can see it did pretty well. Here's the data in the blue, and here's the fit, which has drawn a curve pretty nicely through there. So now you can play some games with it. You can try removing all the, suppose you don't have 2 layers of 64 neurons in the middle. I can go to 1 layer of 64 in the middle. So let's just comment out one of those hidden layers. Whoop, it didn't take my mouse movement correctly. There we go. All right, so now I got 1 input, 64 hidden, and 1 output, just 1 layer. So that's going to be a much simpler model with a lot less parameters. As you can see, instead of having 4,000 parameters, it's only got like 100 now, 195 parameters. And so the end result is still pretty good. But you see, it's not really doing a very good job of following the curve in there. And you can play games here, and I've got some flags to find. Try various combinations here, like 1 hidden layer of 32, 2 of 16, 3 or 4 with only 4, to try various things. And then there's various combinations. So this gives you a start, a simple learning model. You get to practice seeing how well it learns with these sort of structures. So let me stop this recording.